Hello, the screen is visible to everybody. Okay. Am I audible? Hello.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Screen is clearly visible.
Yes, sir.
Yes.
We'll wait for 2 3 minutes. Then
Yes, sir.
Okay. So in the previous lecture, we have started with the synchro as a transducer. We have seen the basic constructional feature of synchro transmitter and how it can be act as a transducer. So basically, synchro is a electromechanical transducer which convert a angular position of shaft into a electrical voltage. Okay, so once again, I just repeat, the construction of synchro transmitter is similar to a construction of three-phase alternator, and operationally, it works on the transformer principle. It works on Faraday's law of electromagnetic induction, where synchro transmitter consisting of two windings. One is rotor winding, another is the stator winding. Stator consisting of three-phase winding which is displaced by 120 degree each apart and connected in star connection. Rotor winding is supplied with a single phase AC supply. Okay, so whenever we are giving input AC supply to the rotor winding, what will happen? It may develop a sinusoidal flux and which can be uniformly distributed over the periphery of your stator. Then, as the stator winding is stationary, so it may cut the flux, and according to Faraday's law of electromagnetic induction, an EMF is induced in the all the three windings, S1, S2, and S3 winding. Okay, so that means your synchro transmitter just behave like a transformer. So rotor winding is act like a primary of the transformer, and your three stator winding S1, S2, and S3 is act like a second. These three winding is just like a secondaries of your transformer. Then we have determined the expression for voltages induced in the S1, S2, and S3 winding. With respect to neutral, then we have determined the line voltages. Okay, so this is then we have seen the how to do the electrical zeroing of this synchro transmitter. I request all the participants please mute their mic. Okay, so how will you do a electrical zeroing of synchro transmitter? Yes, anybody? What is the process? Electrical zeroing. So axis of rotors or here in this diagram, when you coincide the axis of synchro transmitter rotor with the axis of any one winding, so electrical zeroing, you just coincide the rotor axis of your synchro transmitter with the axis of any one winding, then it observes that the voltage is maximum voltage is induced in S2 winding, and the voltage difference of in between S1 and S3 winding is to be zero. So this position is referred to as electrical zero position of your synchro transmitter. And why we are using the electrical zero position? In order to specify the reference in case of position control system. For that purpose, this electrical zeroing is necessary. So this is about the electrical zeroing of synchro transmitter. Okay, then synchro as an error detector. Okay, so how is the electrical connections of synchro as an error detector? Okay, so we have seen potentiometer as an error detector, and in that case we require the two pair of similar pots. So similarly here we require the two pair of synchros. Okay, so therefore one pair of synchro unit, it consisting of two synchro. Unit 1 is called as the transmitter, synchro transmitter, and unit 2 is called as the control transformer, or sometimes it may also called as synchro receiver. Okay, then unit 1, then how to do the connection? So the rotor winding of synchro transmitter is supplied with a single phase AC supply, and the stator winding of synchro transmitter S1, S2, S3 phases are directly connected to the S1, S2 and S3 winding of your synchro receiver, and you are getting the electrical output across the rotor winding of your synchro receiver. Then the rotor of your synchro receiver is directly connected to the load whose position that we have to control. So therefore, the shaft of this synchro receiver is directly connected to the load whose position that we are going to control. So this is all about the simple connections of synchro as an error detector. Then next one is how we are going to discuss about how is the construction of synchro receiver. We have already discussed the construction of synchro transmitter. Only constructionally there is no difference between the synchro transmitter and synchro receiver. Only one difference is there in the rotor construction. The rotor construction of synchro receiver is a cylindrical type. Here I have shown. Okay, so for simplicity, here I have shown the Italian pole type rotor or dumbbell type rotor, but actually the rotor of synchro receiver is not like this. It is just like a cylindrical type rotor. So if you use such type of rotor, and this is your stator, okay, so here you will get a uniform air gap between the stator winding and the rotor winding. Okay, so that is the only difference between constructional difference between synchro transmitter and synchro receiver. Okay, so that means only one difference we have found that synchro transmitter synchro receiver rotor is made up of cylindrical type. So therefore it makes the air gap between stator and rotor to be uniform. Okay, then in the synchro as an error detector, we are getting the electrical output E of T across the rotor winding of synchro receiver. So how it operates? Okay, so now we can understood the principle of operation as a synchro as an error detector. Okay, so please understood this. So when you apply a single phase AC voltage to this rotor winding of synchro transmitter, what will happen? It may develop the flux. I request all the students, please mute their mic. So when single phase AC voltage is applied to the rotor winding, it may develop the flux, and that flux is linking with the stator winding, steady stator winding. Then according to Faraday's law of electromagnetic induction, and voltages are induced in the stator winding. So we have seen that the voltage induced in the stator winding is directly proportional to the cosine of angle between the rotor axis and the stator axis. So therefore, E is proportional to cos of theta. Okay. So then, as the terminals of S1, S2, S3 winding of transmitter and S1, S2, S3 terminals of synchro receiver are directly connected. So hence there is a formation of closed path. Okay, and as there is a formation of closed path, the current may start flowing into this winding. So therefore, current is flowing outward from the S2 winding, whereas in the synchro transmitter stator winding, current are flowing inside the winding. So this is the direction of current which is flowing from the transmitter to the receiver. Okay, so then what will happen at the that means your stator winding of synchro transmitter just providing the input voltages to the receiver stator winding. Okay, and as the input voltage is applied to the stator winding of three phases, the current is drawn by that winding. Okay, then what will happen as current is going to this S1, S2, S3 winding of receiver, it may develop its own magnetic field. Okay, so that magnetic field is swap over this cylindrical type rotor. Okay, then how is the direction of this flux present in the synchro receiver, or the how is the magnetic field linked with this synchro receiver rotor? So which is same as the position of the magnetic field developed by the synchro transmitter rotor. So why is it so? Whatever is the flux direction developed by the synchro transmitter, same type of flux is linking with the synchro receiver. Why is it so? Because the current direction of three-phase stator winding of synchro transmitter is flowing outward, whereas the current flowing through this three-phase stator winding of synchro receiver is flowing inward. So that's why the flux present in the air gap between stator winding of synchro receiver and receiver stator winding and receiver rotor is the same flux that can be present in the synchro transmitter. Okay, so that is why we say that as the flux present in the stator and rotor of synchro receiver is same position as that of the flux present in the synchro transmitter rotor. So therefore, the voltage induced in the synchro receiver winding, we say that the voltage induced is again directly proportional to the cosine of angle between the synchro transmitter rotor and the synchro receiver rotor. So here we consider that, let's say, initial angle of synchro transmitter rotor and synchro receiver rotor is say phi. Okay, so what is the rotor angle you will see at this reference position? Whatever we have considered in the diagram, you see this. We have used this synchro transmitter as under the electrical zero position. Okay, then that means we have coincide the axis of synchro transmitter rotor with the S2 winding and the exactly perpendicular to the at perpendicular position we have kept our synchro receiver rotor. So that means the angle between synchro transmitter rotor and synchro receiver rotor is 90 degree. Okay, so this is the angle between these two rotors. Okay, at the start. So that means the value of phi is 90 degree at the initial position. Okay, so this is the simple fundamental part of synchro as an error detector. So that means we will get the expression for E of t. E is directly proportional to the cos of angle phi, where phi is the angle between the two rotors of synchro transmitter and synchro receiver. So at initial condition, we have kept the value of phi to be 90 degree. Okay. Then we are going to develop. So what is the expression for error voltage E in case of synchro receiver? Okay. So what is the value of E of t? So this proportionality constant is denoted by any constant k. Okay, so therefore we may use the notation k dash because we have used notation k in case of synchro transducer. So it may given by, denoted by k dash. So the voltage induced in control transformer rotor is proportional to cosine of angle between the rotors, two rotors. So therefore it may given by E of t is equal to k dash into RMS voltage applied to the rotor winding of synchro transmitter. So it may be denoted by VR sine of omega t into cos of phi. So this is the required expression for the error voltage which can be developed in the rotor winding of synchro receiver, and the magnitude of the voltage induced in the rotor winding, it depends on the angular difference of the transmitter rotor and the receiver rotor. Okay, so give equation any equation number to this. I may give equation number start to this. Okay, where you can note down what is the value of phi, where phi is the uh, angle between or angular displacement between two rotor two rotors, synchro transmitter rotor and synchro receiver rotor. Okay, then uh, what do we mean by electrical zeroing of synchro transmitter? Okay, so what is the initial rotor angle between transmitter and receiver? In the diagram, what is the value of rotor angle or phi in this diagram? Here you will see that the value of phi is equal to 90 degree. So what is your observations? What is the value of E of t at this condition? Yes, anybody?
0. 0.
0, because you just substitute the value of phi in this expression. So what we are getting, E of t cos 90 is 0. So therefore E of t is 0. Okay, so that is why this position of synchro receiver is called as the electrical zero position. Is called as electrical zero. So why it is called as electrical zero? And how this position can be achieved? How will you do the electrical zeroing of synchro receiver? So simply by making the angle between transmitter rotor and receiver rotor to be 90 degree. Okay, so when phi is equal to 90 degree, the voltage developed across the receiver rotor winding is 0 degree. So that's why this position is referred to as a electrical zero position of synchro receiver. And whenever we are using this synchro as an error detector in any position control system, so over there we are always using at the time of start we are using the always using the electrical zero position, because electrical zero position always represents the reference position. That means we may start measuring our error signal from zero value, and that position is referred to as the reference position. So how will you decide as a reference position? जो पॉइंट से हमें जीरो से वैल्यू मिलने स्टार्ट होते हैं, then such position is referred to as reference position. Okay, so in this way we are making the electrical zero of synchro receiver. So what is the condition for electrical zeroing? Just make the rotor angle to be or the positions of rotor, transmitter rotor and receiver rotor to be perpendicular to each other. So that means we are simply making the angle between transmitter rotor and receiver rotor to be 90 degree. So when you substitute phi is equal to 90 degree, we will get error voltage to be 0. And so this position is referred to as electrical zero in case of synchro receiver. Whereas in case of synchro transmitter, how will you achieve electrical zeroing? By simply coinciding the axis of synchro receiver, sorry, synchro transmitter with the axis of any one winding. So at that time, जो winding के साथ में आपने axis को coincide किया, at that winding we are getting maximum voltage, and if you measure the voltage difference in the remaining two winding, their difference is zero. So this position is referred to as electrical zero of synchro transmitter. So this is all about the electrical zero of synchro transmitter and electrical zero of control transformer. Okay, and this is the expression for error voltage E of T. Then I hope everybody will get this value. Okay, then how will it represent a synchro as an error detector in the block diagram form? Okay, so by using this error voltage E of T, we can develop or we can represent it in the block diagram form. Okay, so here we have specified the electrical zeroing, then we go for the block diagram representation. Okay, so for that purpose, we may consider, because we have this expression E of T is equal to K dash VR sin omega T into cos of phi. Okay, then how will you specify the reference rotor position? Okay, so for that we just take one example. Let's say you have rotated a transmitter rotor in a clockwise direction by certain angle phi. Okay, so what will happen as you rotate this rotor? Let's say it is rotated by theta t. T stands for transmitter. Here I have used the notation theta t. The initial angle between these two rotors is 90 degree. Okay, so as you rotate receiver rotor by angle theta t, what about the position of rotor, receiver rotor? रिसीवर रोटर की पोजीशन क्या होगी? वो रोटेट होगा या नहीं होगा? So as you rotate transmitter rotor, receiver rotor is also rotated in the same direction and by same angle. Okay, so therefore receiver rotor is rotated by angle theta c. Okay, so here I have used theta c. You may use the notation theta r also. C stands for control transformer, R stands for receiver. So that depends on it. Okay, so as you rotate transmitter rotor by theta t, and so same way receiver rotor is rotated in same direction by angle theta c. So initial angle is 90 degree. So what is the new positional angle between these two rotor? As you rotate transmitter rotor by angle theta t in the direction shown in the figure, what is the new value of phi? Or what is the rotor angle between these two rotor, transmitter rotor and receiver rotor? What is the net angular separation between these two rotor? As transmitter rotor is rotated by theta t in a clockwise direction by certain angle theta t. So what will happen as you rotate theta t transmitter rotor? So in the same direction your receiver rotor can be rotating, and then hence the displacement of receiver rotor is theta c. Okay, and this yellow line, this is our reference position. So we always determine the net angular separation with respect to our reference position. Okay, so therefore initially what is the angular separation between these two rotor? It is 90 degree. So therefore phi is equal to 90 minus, what about as you rotate transmitter rotor by theta t? So इसका net angular separation क्या होगा? 90 minus theta t. Okay, so actual position. So here is 90 minus theta t. वो minus हो जाएगा 90 में से, और ये क्या होगा? ये 90 से इधर घूम जाएगा. So ये additional. So with respect to reference, this 90 plus this theta c, so होगा plus theta c. So okay, so therefore here is plus theta c. So this is the net resultant angular separation when you rotate the transmitter rotor by angle theta t. Okay. Then determine the error voltage at this position of rotor. So what you just substitute this value of phi in this equation star. So what you are getting? So we are getting here E of t is equal to k dash VR sine of omega t into cos of 90 minus of here phi is theta t plus theta c. Okay, so you just multiply this, separating out the term in the bracket. So here is k dash VR sine of omega t into cos of here is 90 minus, say multiply karo, it is minus theta c. Then again minus of, sorry, here is theta t minus theta c. Okay, so if you take the minus sign common from these two terms, so what we are getting? So okay, so minus sign common, if you take a minus sign common, so it could be theta t minus theta c. So k dash is equal to VR sine omega t into cos of 90, or you just consider this term as phi term or theta term. Okay, I just consider it is theta. So it could be 90 minus theta. And what is the value of theta? So theta will be given by theta is equal to theta t minus theta c. Am I correct? So this is our required expression. E of t is equal to k dash VR sine omega t cos of 90 minus theta. And what is the value of cos 90 minus theta? What is cos 90 minus theta? What is the trigonometric formula? Cos 90 minus theta. I thought it could be sine theta. Please check the formula. Okay, so cos 90 minus theta equal to sine theta. So therefore, this E of t is given by k dash VR sine of omega t into sine of theta. Okay, so this is our new expression. So error voltage is given by where this k dash VR sine omega t. This is the constant term. So therefore, we may use another constant to represent it. Okay, so it can be represented by another constant. So therefore, we may define E of t is equal to ks times sine of theta, where theta is theta t minus theta c, where this ks is called as the sensitivity of error detector. Sensitivity of error detector, or which is also called as constant. Okay, then again we can simplify this equation. So for smaller value of, so sinusoidal, this is the sinusoidal signal. Okay, so when theta t minus theta c, if you refer for very small angle, say 10 to 15 degree, for this angle, the change in signal value is very small. Okay, so for that purpose, we may consider that sine of theta t minus theta c. Okay, so for small value of angular change, we say that the sine of theta t minus theta c is nearly equal to only theta t minus theta c. So this is the approximation we are making here. This is for smaller angular change because mostly in most of the application, this synchro as a error detector, this can be used for 10 to 15-degree angular change detection. We can detect the position for the case of 0 to 15 degree. So for that purpose, this sign of theta t minus theta c is denoted by theta t minus theta c. This is for small angular change. Okay, so therefore we say that for smaller angular displacement, theta t minus theta c or sine of theta t minus theta c is nearly equal to simply theta t minus theta c. Okay, so therefore with this approximation, we'll get the other expression for E of t. So E of t is represented by Ks times simple theta t minus theta c. So this is our new expression. Okay, where this Ks is called sensitivity, or which is also called as the gain of your error detector. So again, you can note down. This may also we may call it as gain. Okay. Then what is transfer function? By definition, it is the Laplace transform of output to the Laplace transform of input. Okay. So what is the output of error detector? एरर डिटेक्टर का आउटपुट क्या है? That is E of t. So simply take the Laplace transform of E of t, that will give you E of s. Okay. So give any double star notation for this. Simply take the Laplace transform of this equation double star. So you are getting E of s is equal to Ks in bracket theta t of s minus theta c of s. Okay, so therefore you will get the expression for so here E of s is the Laplace of output and theta t of s minus theta c of s. So this is your input. Okay, so the input to the receiver is nothing but it is the angular difference of two rotor positions. So therefore the transfer function will be given by the ratio of E of s upon theta t of s minus theta c of s, and that is nothing but Ks. So this is the required transfer function of synchro as an error detector. So now represent it in the block diagram form. Okay, so how is the block diagram representation? So what is the input? As we are using here the angular position control, and synchro is the electromechanical transducer, so it converts the mechanical angular position into electrical signal. So therefore input is here theta t of s, then here is error signal, error detector, another input is theta c of s. So this signal magnitude is minus, then multiply it with Ks. So this would be your E of s. So give the figure name to block diagram of synchro as an error detector. Synchro as an error detector. So that means a simple pair of synchro, that is physical pair of synchro in the control system is represented by simply this block diagram. So that means this is the representation of synchro as an error detector in the block diagram, where theta t is the angular displacement with respect to transmitter and theta c is the angular displacement with respect to rotor, where Ks is the sensitivity of synchro transmitter or its gain. Okay, so where is the applications of this synchro transmitter or synchro as a error detector. So generally, synchro as a error detector, it can be used in the servo mechanism for the torque transmission purpose. This is the one of the popular application of synchro as a error detector in the servo mechanism for torque transmission purpose. Then sometimes it may use in the weapon system. Then again it can be used in the antenna position detector. Okay, so these are the few applications of synchro as an error detector. So some many times in the examination, one question always asked based on this. Titan explains synchro as a transducer or Titan explains synchro as an error detector. So what is expected in the synchro as an error detector? You always give the constructional difference between synchro transmitter and synchro receiver. Then simply explain the working principle of this synchro as an error detector. As you apply input voltage to the rotor of synchro transmitter, it may develop the flux and that can swap over the stator of synchro transmitter. Then according to Faraday's law of electromagnetism, as flux is cut by the stator winding, it may develop the EMF, and the direction the magnitude of induced EMF is directly proportional to the cosine of angle between the rotor axis and the stator winding axis. That is theta. Okay. Then the voltage induced in S1, S2 winding is directly applied to the stator winding of the receiver. That means stator winding of transmitter provides input, electrical input to the stator winding of synchro receiver. And as the current is flowing to the receiver rotor winding, it may develop the magnetic field. Okay, and that magnetic field is swap over the cylindrical type rotor as because the air gap. So we have used the cylindrical type rotor to make the air gap uniform. Okay, then the what is the flux present in between stator winding of receiver and the rotor winding of receiver is the same position as that of the flux present in the transmitter rotor. So that is why the error voltage developed in the rotor winding, which is directly proportional to the cosine of angular difference between the transmitter rotor and the receiver rotor. So this is the simple working principle. And then justify the electrical zeroing of control transformer and then derive the block diagram. You just make this approximate. So this is all about the synchro as an error detector. If you have any doubt, you can ask me. Then we may go for next point, that is DC tachogenerator. So next element in unit 2 is DC and AC tachogenerator. So this is a very small point, tachogenerator. So where you can use this, what is the function of tachometer? Yes. Have you used the tachometer in the laboratories? Yes, anybody?
Sir, to measure the speed.
Right. Okay. So for measuring the speed, we are using a tachometer in the laboratory. That means tachometer converts what? A speed is converted into a simple number. Okay. But what is the application of this tachogenerator? Okay. So why the name is given to this tachogenerator? I just give you one example. Suppose if you want to do a automatic speed control system. Okay, so how will you do it? Or say, so another simple example I just give you. Because speed is a mechanical quantity. Okay, and if you want to implement any digital type of control system, okay, so how computer can understand a mechanical quantity, because processor or computer doesn't understood the uh, torque or the speed mechanical quantity. It can understood only a electrical quantity, that to be in the form of zeros and one. Okay, so for that purpose, it is necessary, when you are developing any kind of control system, it is necessary to convert mechanical quantities into electrical quantity. So for that purpose, we require a transducer. Okay, so therefore this is again one kind of transducer. So the basic function of this transducer is that DC generator is again, it is a electromechanical transducer which convert angular position of shaft into a electrical voltage. Okay, so for that purpose these DC tachogenerators are used. So that means input to the tachogenerator is the speed, and that can be converted into a electrical voltage. And once you convert a mechanical quantity into electrical voltage, so that can be easily read by any processor simply by converting into a binary value. Okay, so this is a simple function of DC tachogenerator. So wherever you want to measure the speed, okay, and convert it into a digital value, over there it is necessary to use the DC tachogenerator or AC tachogenerator. So depending upon the application, you can use. Okay, so this is about the DC tachogenerator. So therefore, we say that DC tachogenerator is nothing but the electromechanical transducer which convert a rotational speed into a proportional DC voltage. Okay, then how is the constructional detail of this DC tachogenerator? So its constructional detail is very simple one. It consisting of a simple pair of permanent magnet. Let's say this is North Pole and this could be your South Pole. Okay, and in between this permanent magnet, we just place the armature. Okay, so these are the brushes of your armature, and across these brushes, we are getting the electrical voltage. Okay, or this is your output voltage E. Okay, and then what is the input to the shaft? So the armature of this DC tachogenerator is directly attached to the shaft whose speed that we have to measure. Okay, so this is a simple figure for DC tachogenerator. DC tachogenerator. Now, how it works, on which principle basically it works? Can you justify from this diagram? Can you guess? So here, this tachogenerator rotor is directly attached to the shaft, that speed that we have to measure. Okay, and this armature is placed in a magnetic field. Here we have used the permanent magnet, so that means these are the flux lines. So magnetic field is permanently present. Okay, so therefore what will happen, as the armature of tachogenerator is attached to the shaft and this shaft is rotating, so that means your armature conductors are also rotating. Okay, so as armature conductors are rotating, it may cut the flux, and then according to Faraday's law, as the conductor cuts the flux line, and EMF is induced in that conductor. So therefore, at the output, we are getting the value of E. Then at which factor this magnitude of E is present depends. So generally, the magnitude of E is directly proportional to the angular speed of your shaft. So as the shaft speed reduces, the magnitude of the output voltage reduces. As the angular speed increases, the output voltage also increases. So therefore, we say that the magnitude of the voltage is directly proportional to the angular velocity of the shaft. Again, one more question is that this output voltage has polarity, positive and negative. So the polarity of this voltage depends on which parameter? how will you change the polarity? So if you simply change the direction of the rotation of the shaft, the polarity of output voltage is also changing one. Okay. So therefore, the polarity of voltage induced, it depends on the rotation of the shaft. Okay. So therefore, as E is directly proportional to omega, okay. So therefore, this proportionality constant is denoted by any other constant. We may denote it by tachogenerator constant. So we may consider it by KTG. Okay, so E is equal to KTG times omega. Okay, where this KTG is called as tachogenerator constant. Okay, so therefore, how will you represent it in the block diagram form representation? So simply take the Laplace transform of this equation. So here we are getting E of S equal to KTG times omega of S. Okay, so what is the input to the tachogenerator? Input is the omega angular speed and output is the electrical voltage. Therefore, transfer function is nothing but, in case of tachogenerator, ratio of Laplace of output, that is E of S upon Laplace of input. So input is the angular speed. So E of S upon omega of S is the KT. So this is the simple transfer function of DC tachogenerator. So then it can be represented in block diagram form. Okay. So input is omega of S, then this is tachogenerator constant ATG, and output is E of S. In this way you can, so this is the block diagram representation of tachogenerator. So then this is for DC case. Suppose if you want to use this DC tachogenerator in case of AC case, so simply whatever is the output we are getting, so that output you can apply to the modulator. Then this modulator can convert your DC output into a AC output. So same DC tachogenerator can be used in case of AC system also, simply by using this modulator. Okay, so which is basically a inverter which converts a DC voltage into a AC voltage. So this is all about the DC tachogenerator. Then second type of tachogenerator is AC tachogenerator. Okay, we just discuss about it, the construction and working principle. Do you have any doubt in DC tachogenerator construction and working? Okay, so in short, we are going to discuss it. So what is AC tachogenerator? Again, AC tachogenerator is a electromechanical device which convert a mechanical angular position into a electrical voltage, or we say that it converts a rotational speed of the shaft into a electrical AC voltage. Then on which principle it works? So basically it works on the induction generator principle. So how is the electrical diagram of AC tachogenerator? Okay, so then it will clear to you. This is the rotor of your AC tachogenerator, and the rotor of tachogenerator is directly attached to the shaft whose speed we are going to measure. Let's say this is omega. This is the shaft whose speed we are going to convert into an electrical AC voltage, and it consisting of two windings. Okay, so this winding is called as the reference winding, and the second winding is called as the output winding, and across this winding we are getting the output voltage E. So that's why this winding is called as the output winding. Okay, so this is a simple figure for AC tacho generator. So how is the principle of operation of AC tacho generator? So in AC tacho generator, you just attach the rotor of AC tacho generator to the shaft whose speed is to be measured. Okay, so as the rotor of AC tacho generator start rotating, then what is the function of this reference winding and output winding? So reference winding is also called as the main winding, and this winding is supplied from a single phase supply. Okay, so input voltage is applied to the reference winding, and from the output winding, we are taking the electrical AC voltage. Okay, then how will you get a AC voltage? Or how it basically works? Okay, then what will happen as you apply input to the reference winding? It may develop the flux, and that flux is linking with the rotating rotor. Okay, then what will happen as the flux is cut by the rotor conductor and EMF is induced in the rotor conductor, and generally the rotor construction is squirrel cage type. Okay, so you know the construction of squirrel cage type rotor. The rotor conductors are short circuited at both the end with the help of end ring. So therefore, current start flowing through the rotor conductor, and it may also develop its own field, rotor field. Rotor field is get developed, and that rotor field is linking with this output winding. Okay, and as the rotor flux is linking with this output winding, then AC voltage is developed, and the magnitude of this AC voltage E, it depends on the speed of the rotation of your rotor. So as the speed increases, the magnitude of AC voltage also increases. As the speed decreases, the magnitude of AC voltage gets decreases. So that means the amplitude and phase of the output voltage, it depends on the direction of rotation and the speed. Okay, so therefore, again, in case of AC tacho generator, we say that this E is directly proportional to the omega. Okay, so again, same way you can consider where KTG is the tacho generator constant. Then take the Laplace transform of this. So again, you will get transfer function E of S upon omega of S. Okay, equal to KT. So this is again block diagram representation of AC tacho generator. Then suppose if you want to use AC tacho generator in case of DC system, you want DC output. So what we are doing at the output winding, you just apply connect a rectifier and convert a AC signal into a DC signal. So same AC tacho generator you can use for the DC case also. Okay, so this is all about the tacho generator, AC tacho generator and the DC tacho generator. Okay, so only one point is remaining in the unit 2, that is stepper motor. So in the next lecture, we are going to discuss about stepper motor, and we may switch to next unit, that is unit 3, time response analysis. Okay, so if you have any doubt, you can ask me. So today we stop here. In the next lecture, we can discuss about stepper motor. Do you have any doubt?